The objective of this video is to introduce Middlebrook's extra element theorem. Middlebrook was one of the pioneers of power electronics. He was a professor at Caltech, a well-known teacher and a consultant within the field. And this is a technique that he developed to study how a linear circuit behaves when you add another element to the circuit. So maybe you're taking an inductor and a resistive circuit and adding a capacitor to it, or maybe you're adding a more complex feedback network. But the idea is that this is a tool to evaluate a system transfer function when we want to add a new impedance. And the basic idea of this is that, well, when you add a new impedance to a circuit, you could rederive the entire transfer function. However, this tool gives you a mechanism to calculate the transfer function without having to rederive the entire circuit transfer function from scratch. So this is a common thing that occurs in power electronic circuits. You've got your circuit and you decide, oh, it's not filtering the output voltage well enough. What if I were to add an extra capacitor here? What if I were to add an extra inductor there? This tool gives you a mechanism to quickly modify your transfer function to account for this new element and allows you to quickly evaluate its frequency response. So this is a time-saving tool. And we're going to start by talking about it in a very general theoretical sense, and then we'll work our way to concrete example problems. So on the left side, you'll see that I've sketched a block diagram of a potential system. We have an input, U of S, on the left side. On the right side, we have an output, Y of S. And this input and output, it could be anything. It could be the input could be a voltage, like voltage input, or it could be a duty ratio. Well, the output could be an output current or an output voltage. In fact, this need not even be strictly a circuit. Perhaps the input is torque and the output is speed. But the key defining feature of this is that the system has some electric circuit portion to it, and it exposes an electric port. So that's what we've labeled down below. So somehow there are circuit elements within here, and the generic basic question that we're trying to answer is, what if I were to connect a new impedance across this electric port? And the impedance has a value Z of S. This could be a resistor, it could be an inductor, it could be a capacitor, it could be a combination of all three. And the question again is, how do we calculate our system transfer function? If we know it when we do not have the impedance, what does it become when we have our impedance? And it turns out we can express this in terms of the original transfer function plus a correction factor, or multiplied by a correction factor. So if our system transfer function is G of S, which is Y of S divided by U of S, it can be expressed as G of S evaluated when Z of S is equal to infinity. So again, if Z of S is equal to infinity, that corresponds to the case where we have no impedance added here. That was the original transfer function. So we take our original transfer function and then we multiply it by a correction factor. And that correction factor is of this form. So this is the extra element theorem result. Let's now define what the terms in here mean. So we already know what Z of S is. That is the impedance that we're adding at our electric port. Next question is, what are ZD of S and Zn of S? ZD of S, or just ZD, is the driving point impedance when we have a null input. And what does that mean? Well, if we were to take our block diagram and sketch it in a more compact form down here, a null input simply means that the input to our system is 0. So if our input is 0, and then we have whatever our output is, we then calculate the impedance as seen at our electric port terminals by injecting some kind of sample current signal and measuring the resulting voltage that appears across it. So this is the same thing that your multimeter does. If you attach a multimeter to a circuit, it injects a current and it measures a voltage. That's what we're doing here. We're measuring the impedance seen at the electric port of our circuit. And we can write this as ZD is equal to V over I when our input is 0. And you can remember where the driving point impedance goes in our circuit because it has a D in the denominator. The next term is Zn, which is our nulled output driving point impedance. So what does that mean? Let's sketch our block diagram again. This time, instead of the input being null, our output is null. So our output is 0. And the idea is that this is the impedance seen at our electric port terminals when we inject a current that causes our output to be 0 for any input signal. So this means that if you were to give me some arbitrary input on here, I'm going to cause a current to flow at the electric port terminal so that the output is 0, and then I'm going to measure the output, then I'm going to measure the impedance seen at the input. So you give me an input, I flow a current that makes sure that my output is 0, and then I measure my electric port voltage, and I divide the voltage by current to get the impedance at the electric port again. So we can write this as Zn is equal to the voltage at our electric port divided by our current, but this time our output is 0. Okay, so at this point, I'm sure this sounds like a fairly abstract concept to you. Let's now make it concrete by working through a few examples. The first example I want to consider is a circuit that we've been discussing over the last couple videos. And that is the simple inductor resistance network. And let's suppose that we want to modify this circuit by adding a capacitor in parallel with the resistor. So that is, we're going to add an impedance, Z equal 1 by SC, which is the impedance of a capacitor. So if we derive the transfer function for this, using the extra element theorem, we can express it in terms of G when Z is equal to infinity. So that's the first term up here. And then we can add in the second term over here. So we've spent considerable time deriving this transfer function, and you'll recall that we can express it as a simple pole. Meanwhile, we can start by deriving our driving point impedance for a null input. So a null input for this circuit means that we have shorted our input connection, and we're going to look at the impedance between these terminals. So if we were to inject a current I, we can measure the voltage that's going to appear across here to determine our input impedance. And clearly in this case, it's a very simple expression. It's just our inductor impedance in parallel with our resistance. Next, we can talk about our nulled driving impedance, Zn. And this is the null driving impedance corresponds to the case where output voltage is 0. And if our output voltage is 0, we effectively have a short across this node here, which means that no matter what current we flow into our terminals, we're going to see 0 impedance. So we have 0 ohms here. And finally, the impedance of our capacitor, we already know, it's 1 over SC. So we're now ready to populate the fields using the extra element theorem. So Zn was 0. And Zd was our inductor in parallel to the resistor, divided by Z gives us a transfer function. we can now condition this transfer function to get it into the pole zero form that we've been talking about in our previous video. Oftentimes when you use the extra element theorem, it immediately results in the transfer function in fact being in pole zero form. In these cases, this is a very handy tool because you don't even need to condition your circuit. You immediately know where the poles and zeros are located that your new element is introduced. I'm now going to show you an example where that is the case. Suppose that I've given you this circuit here, and I want you to try this exercise on your own. So I'm going to lead you through a set of steps, and as usual, press pause when you're ready to begin and press play when you're ready to resume, but not quite yet. Let me set the problem up a little bit further. So suppose that your goal is to initially to find the transfer function when the impedance Z is equal to infinity. So that is when the capacitor has been removed from the circuit and the transfer function is relating V out to V in. So that is, find your initial transfer function of the circuit before adding Z. Press pause now and play when you're ready to resume. You should have found the following transfer function, which is just a simple gain. This is just a simple voltage divider if the capacitor is not present. Now I want you to find the driving point impedance of this circuit. That is, find ZD. Press pause now and play when you're ready to resume. You should have found the following impedance for the circuit. And you should have done this by realizing that the driving point impedance implies that you have a short across the input voltage. At this point, as seen from the terminals of the capacitor, the impedance is R2 plus the parallel combination of R1 in parallel with R3 plus R4. Now I want you to find the nulled output driving point impedance, Zn. Press pause and press play when you're ready to resume. So this was probably the trickiest part of the problem. The nulled output driving point impedance implies that our output voltage, V0, is equal to 0 volts. And if V0 is equal to 0 volts, that means that I4 must be 0 because there's no voltage drop across R4. And if I4 is 0, that means that the current through resistor 3 is 0, which means that V3 must be equal to V out, which must be equal to 0. So if V3 is 0, we effectively have a short across this point, which means that when we inject a current at the terminals of our capacitor, so when we inject a current, we replace our capacitor with a current source, that the voltage that we're going to see across these terminals is going to be our current source multiplied by R2. So V is equal to I times R2, where I is the value of a current source that we're injecting, and V is the voltage that we're measuring across the terminals. And this means that Zn is equal to R2. So finally, use the extra element theorem to find G2, the final transfer function, when our capacitor is present. Press pause now and press play when you're ready to resume. So you can see that in this case, the extra element theorem has given us our circuit transfer function in pole zero form, which is very convenient. Finally, in summary, I want to again point out that all of these results that we derived today, all of the, in both examples, the transfer functions that we derived today, we could have found them out by considering the final circuit directly. We could have directly derived the transfer function of the final circuit in example 2 that has the capacitor and the final circuit in example 1 that has the capacitor. And we would have gotten an equivalent result. However, when we already have the transfer function of the circuit without the capacitor present, we save ourselves a lot of effort by using the extra element theorem to find the new transfer function. This is yet again another tool that we are building up in our repertoire to use for studying linear circuits and the closed loop regulation of power converters.